All right, hello and welcome to your first lesson for NTI, which is over the definition of an integral on week 1. Before, we were looking at the purpose of an integral and how we were able to undo the derivative. There's a lot of confusing notation in this integral, especially this strange s. But if we look a little bit closer at what this is telling us, if we take each piece, then we'll see what we're actually looking at is, for radical 1 minus x squared, a semicircle, which you can see at the bottom of your screen. I'm highlighting it in pink. And that's just the y values for the semicircle. And if we look at the y values, this is just the y height of the function. We've discussed this before with related rates and with optimization. It's not too hard to see that, oh yeah, that function is just giving us a bunch of y values. That's what y is. It's represented by that function. So that piece isn't too hard to understand. But if we look at dx, this is the change in x, this delta x, and delta x gets really small. And it's getting really small, kind of defined by a limit. And if we take, if you look down at the semicircle we have, if we take the distance between those x values, we're going to start to accumulate a lot of different areas because we have multiplication between the y value, the pink thing, and the yellow thing, the dx. So we have a y times an x. Now, what does this symbol over here mean? It means sum. This yellow s is just a representation mathematicians use to represent sum. So what we're actually doing is we're summing together the pink y values with the yellow x values. And we're going to sum those things together between the bounds x equals -1 and x equals 1. You can see -1 and 1 on your left and on your right. So we'll find the area under that curve. Now, because we're just finding the area per se, it doesn't really that doesn't really make a lot of sense because the area, our area, or x times y, could be negative. But we'll look more at that in the future. Now, what if we were to take the change in x to be 0.25? So we have these 8 rectangles. So we don't actually have an infinite amount of area or an infinite amount of rectangles defined by a really, really small delta x like we had in that notation up there. Well, we would get some gaps, and we could maybe move those gaps around to fill in this whole area under the curve, under this semicircle. But that would be a little tricky. We'll increase the amount of rectangles, and we'll decrease the change in x. So we'll use 0.125, and we'll see this is a little bit better. We've got some more area to displace. We'll have a little bit better of approximation, but we really can't get any better than just taking the area under the curve as delta x gets very small. So we want to find the exact area. So we'll take delta x getting really small. And that's not too bad with this semicircle if we don't use rectangles. But this here is your definition of the integral. It's just the y values multiplied by the change in the x values. Now, what we want to look at now is representation of f of t. But before that, we can't actually integrate radical 1 minus x squared. We would have to use u substitution, and we don't know anything. We don't have the appropriate du in this. So we'll look at our examples and what you'll work on in this sense, in graphical form. So if we start with number 1, we want to look at the integral from 0 to 3 of our function f of t. So we'll take the bound starting at 0 and going all the way to 3, and the area between those two things, the y values defined by f of t and the x values multiplied together, and we'll get an area of 1 starting in this block, and then we add it with 2, so the second block, and we have a third block in this area, and of course the other two blocks make 4. So we have a total of 4 units that make up the area. So our answer to this integral from 0 to 3 is 4, because I'm taking the y values times x values. Now if we look at the next example from 3 to 6, we're adding up a negative area because it's under the x-axis, and I'm just going to shift around some pieces of my units to represent the area a little bit more concretely. And we notice I've got half of a unit with that triangle, and then the other unit becomes a full unit if I move around some other triangles. Now be careful, because this is an area of 1.5. It has to be negative 1.5 because we're multiplying negative y values to positive x values. Now if we just don't look at the graph for a second, if I'm adding up the area between 0 to 6, and I'm taking my start bound to be 0 and carrying that on to 3, and then from 3 to 6, then I'm actually looking at this first integral from 0 to 3 plus the second integral from 3 to 6. So I'm just adding 4 and negative 1.5 together. And of course, I'm going to get 2.5. Now for number 4, this one looks a little funny because I've got a start value of 6 and an end value of 3. And I want to make sure we're looking at this right. So if you don't look out for this, it's very easily missed. But if I start at 6 and go backwards towards 3, then I'm going to actually be multiplying a negative x value times a negative y value in this case. So I'll end up with 1.5. Now you might find it strange that we have negative area, or we're talking about negative area, but what we're actually doing is we're just multiplying x and y values together. It's just conceptualized with area. That's also why I'm not including units, because I'm just multiplying an x times a y. Now let's look at this negative 3 to 0. I'm not going underneath the x-axis. I'm still above the x-axis, and I'm finding the area under this curve. And I'm going to break it up into different regions. And I know that that block is 4, and this here is 4, because I can move around some triangles and units. But this slender triangle on my left, I don't want to think too hard. I've got 1/2 base times height locked away. I know that's area of a triangle. So I'll take my 1/2 times, let's see, 1 unit is my base and 6 is my height. I'll have 3. I'll have 3 units in total. So altogether, I'll have 11 units. And this one's a little strange because I'm in the negative x region, but don't let that fool you. We're still going from left to right, so we're starting at -3 and we're ending at 0. Now, this piece, this last one, 6, is taking from 6 to 8, the area under that piece of our function. So that's going to be a quarter of a circle, and I'll use pi r squared and divide that by 4. So if I divide my area in 4, I will get the quarter of the circle that exists between 6 and 8 that's bounded. So I'll end up with pi. So that there is your basically skill that you're looking at. You're using the notation in an integral, so the y values, f of t here, to determine the area under the curve. So be careful when you read these, and I will post the homework on Google Classroom, as well as putting it right here for you. So we've got the appropriate, it's not really homework, but the appropriate work for you to try out. And you can definitely ask me questions about it. I'll be online and you'll get a lot of communication from me.